Welcome to your 7.4 section on logarithms. In previous lessons, you may have had an exponential that ended up in the form of a equals the initial amount, 3,300, times the growth factor of 1.04 all raised to the t, where a is the amount of money after a certain number of t years. If I asked you in what year the money exceeded $4,000, so in what year did the money actually achieve $4,000, there really isn't a way to algebraically solve the problem. I mean, for example, if I were to put 4,000 in, 4,000 is the amount after that many years. So I'm going to go ahead and write in between the two graphs that I have. If I have 4,000 is equal to 3,300 times 1.04 to the t, there really isn't a way that you know right now that actually helps you solve for an exponent where the variable is actually in the exponent. Okay, the best that we could do right now is pull out our graphing calculator, graph the exponential function that's on the right side, 3,300, 1.04 to the t, and then get that nice exponential graph, and then make a second equation of a line, a horizontal line of 4,000, and find where those two lines intersect, or two functions intersect. Okay, well, that's not very efficient. I don't want to have to do that. I want to know what I actually have to do to go ahead and algebraically solve it versus having to go depend on a graph. So the answer to that question is something called logarithms. Okay, at the very bottom of the screen, you see that logarithms can also be called logarithmic functions, okay, or even simply logs. So we'll actually refer to it as logs quite a bit. You'll see the word log come up. Okay, that just is a simplified form of logarithms. So for example, you know that 2 squared is 4, that's easy, and 2 cubed is 8. But what if I ask you 2 to the what gives you 6? Well, we know that 6 is between 4 and 8. And so that would make sense that when I do 2 squared to get 4 and do 2 cubed to get 8, I know that my 2 to something, probably between 2 and 3, must produce 6. But I don't have a nice integer value to actually go ahead and give me the result. And so logarithms are the piece of the puzzle that we need in order for us to solve for when we have a variable in the exponent that we actually want to find. So when you look at something like this, when I have this white box here, there's a lot of information right here. So what I want to make sure that you do is if you ever need to pause and reread some of this, please do. What I'm going to focus on is what's directly in the middle. And more specifically, I'm going to go in reverse order. So if you look directly in the middle, you see two equations with an if and only if in between them. What I first want to do is look at the second one. I have b to the x is equal to y. Okay, first of all, in the sentence above, I know that b and y are just numbers that are positive, with b definitely not equaling 1. So you can think about that being 2 to the x equals whatever, 6 in this case. Okay, so b and y are numbers. If I want to solve for x, if I want to solve for the variable x, I need to get it out of the power, and logs help us do that. So you can see that that the b of x is equal to y, b to the x is equal to y, is equivalent to saying what's on the left side of the screen, which is log base b of y is equal to x. So again, you can see it's in quotations right below, log base b of y, okay, is equal to x. The cool thing is that they relate pretty easily. If you're given the log function, what's on the left, compared to the exponent notation, which is on the right, okay, you can actually go ahead and can go between them pretty easily. For example, if you look at the left side, I have log base b. Base b, that's the same thing we talked about with exponents. B is the base. So if I go ahead and take b and I raise it to the x, I know I'm going to get out y. So it's a kind of a cool little technique that I offer to my students in terms of a nice little cycle here. The base to the answer x is equal to y. And so if you do that, you can go ahead and convert between them both. Okay, more simply, I summarize it again below. If you have something like this, okay, b to the x is equal to y, we call that to be an exponential form or exponent form, is equivalent to log base b of y is equal to x. Again, why? Because I can take b and raise it to the x, and that's going to give me out y. Kind of a nice rotation there when you're in logarithmic form. So let's try a few. Okay, I want to rewrite them. I want to be able to move between logarithmic and exponential form relatively easily. So if I have a logarithmic form, again, it might be helpful for you to pause and be able to pronounce this. The first one is log base 2 of 32 is equal to 5. Well, according to what I was doing in the previous slide, I'm going to take the base, which is 2, raise it to the answer, and I'm going to go ahead and get out 32. So if I want to put an exponential form, okay, I want to say 2 to the 5th power is equal to 32. And it's exactly true, because 2 to the 5th definitely is 32. The one down here, the next one down, log base 10 of 1 is equal to 0. Well, if I take the base 10, raise it to 0, I should get out 1. So if I come back over to the exponential form, I should get 10 to the 0 power is definitely equal to 1. Okay, that is definitely true. What if I spin it the other way? What if I go 9 to the 1st power is 9? Well, we definitely know that's the case. And generally what I like to do is I like to set up the problem. So I'll put in the log, I'll leave some space, and I'll put a little equal sign. So I have 3 numbers to fill in. I fill in the base, the number next to the base, as well as the answer. Well, if you look at what we've done before, the little number, the subscript number, is always the base. Well, if you come over to my exponential form, I think my base is 9. So I'm going to go log base 9. Now you got to ask yourself, 9 to the what gave me 9 back? Well, I think 9, if I go ahead and kind of keep the same pattern, to the 1st power gives me back 9. So log base 9 of 9 gives me 1. Let's try one more. What if I give you 1/5 to the negative 2 is 25? If you check that in your calculator, that's true. Again, if I want to convert it to a logarithmic form, I'm going to do a log. I'm going to put a little equal sign in there. Okay. Again, the base is the same, so the base is 1/5. So when I do log base 1/5, raised to the what gives me my answer? Well, it's 1/5 raised to the negative 2, according to the exponential form, should give me out 25. Okay, so we need to be good at rotating between both logarithmic form and exponential form. Okay, now what if I do this? What if I want to evaluate these logs without the use of a calculator? Well, what I like to do, especially like in number 1, is I want the answer to that. I don't know it yet, so if I don't know something, I generally like to call it x. So I want to know the answer of log base 3 of 81 is equal to x. The reason why I do that is because now I can go ahead and do my little kind of cycle. Okay, 3 to the x is equal to 81. So if I convert it to exponential form, I really have 3 to the x equals 81. Those are identical statements. One's just in log form and the other one's in exponential form. So now it's a little bit of work, so especially without a use of a calculator. But if I do 3 to the x equals 81, I think if I go ahead and keep doing that over and over to 3 to the 1st, well, that's 3. 3 squared is 9. 3 to the 3rd, 27. 3 to the 4th, I think, is 81. So I think x equals 4 in this case. Okay, the next one, I'm going to equal my answer to x. So I have 1/4 to the x is equal to 256. So again, if I go ahead and do exponent form, 1/4 to the x power is equal to 256. When I do that, I got to ask myself, okay, I have 1/4. I want to end up with a whole number versus another fraction, so it must be a negative value. And when I do that, and you can verify it in your calculator, I think if I raise it to the negative 4, okay, think about it, if I have a negative exponent, I'm going to flip that 4 back up to the top, and 4 to the 4th is 256. There's my answer. Okay, let's do another one. This is equal to x, so 10 to the x is equal to 0.001. So again, 10 to the x is equal to 0.001. Well, if I want to go ahead and turn 10 and move it over 3 decimal points, I think I'm going to go ahead and get x equals -3. And then finally, the last one, 64 to the x is equal to 2. 64 to the x is equal to 2. Again, you got to ask yourself, I want to take a big number, 64, and get it back to a smaller number of 2, which means I probably need some sort of fractional exponent, which a fractional exponent really means I have a root of some sort. So 2 to the what gives me 64, and I think 6 does. And so if I raise 64 to the 1/6, so take the 6th root of 64, I'm going to get my answer of x equals 1/6. This screen looks a lot more intimidating than it actually needs to be. Okay, it's just some common lingo that we all need to know. Okay, and again, in the middle of the screen is where I'm going to focus. Okay, one's called a common logarithm, the other one's called the natural logarithm. Okay, in either case, it's just a matter of how we write things. On the left side, the common logarithm just means this. Instead of writing log base 10, we're simply going to write log instead. If you ever see log, we automatically know, we assume in math that we are already at a base 10 model. Okay, and so we're not going to go ahead and actually write 10. It's redundant. It's kind of like instead of writing 1 times x, we simply just write x, because the 1 is not needed because the existence of x in the first place implies we have 1 there. Okay, same thing for the logs. Okay, when you have a log base 10, if the log is there and there's no base, we can assume that to be a base 10 there, so we can put it in if we need to. On the other side, we also have something called a natural logarithm. Okay, you can see that we have an e there. We talked about that last section in terms of that e number. Okay, if we have a log base e, we actually have a function in our calculator called the natural log, or ln. Okay, and so if you see ln, that means log base e. And so just know that if you see this plain old log, it's base 10. If you see ln, that really means log base e. Let's actually do a couple of these. I want to make sure you know where things are in your calculator. So if you have your calculator out, that'd be great, or else pause the video and come back. You can see here, if I look at something like this, I want to go ahead and evaluate the following using a calculator. Okay, so you can immediately see that I brought my calculator up, and you can find that there's 2 buttons on your graphing calculator that show you log as well as natural log. And it's on the far left column, and it's the 3rd and 4th buttons from the bottom left. Okay, and so if I want to calculate log of 0.85, I'm simply going to press log of 0.85, hit enter. And I should get, if I go back to my problem now, okay, I should get an answer of negative 0.07. Okay, now we can check that, because we know if it just says log, that really means I have log base 10 of 0.85 is equal to negative 0.07. So you can always check yourself, because the cycle should still work. I should be able to raise 10 to that answer, should give me back 0.85. So let's check it. If I go back to my calculator, I should be able to say 10 raised to that previous answer, so second negative, okay, better give me back 0.85, which it does. So I just found out when I raise, if I go back to my green screen, I know that when I take 10 and I raise it to the negative 0.07, I know for sure I'm getting out 0.85, which is pretty slick. Okay, let's try one more. Okay, natural log of 22, go back to my calculator, I'll clear my screen. Natural log is the 3rd button from the bottom, so natural log of 22. And I hit enter, and I easily get 3.09. Again, what's that actually mean? Natural log really means log base e of 22 equals 3.09. And so if I do my cycle, e to 3.09 is equal to 22. In other words, e to the 3.09 better give me out 22. Again, we can check that. Okay, your e is the 2nd function of the natural log. So if I clear out my screen, second, I probably should have done that because I want my final answer again. So I'll redo it. I'll do natural log of 22. Get that decimal back because I want to use that. So I'm going to do second natural log to get e to the x. I want to do e to that previous answer. And I should get back 22, which I do. Okay, all of this should work together. Okay, finally, the last thing we're going to do today is something called inverse functions. Okay, we know what inverse functions are. We know that inverse functions reflect over the y equals x line, but more importantly, we know that when we put one inside the other, they always produce x. Okay, and so you can see here, okay, by definition, the function x equals log base b of y is the inverse of the exponential function y equals b to the x. Which again makes sense, because if I do the cycle notation, if I go base b, raise the answer is equal to y, that's exactly what this says down over here. So what it's saying is that those 2 models, when I put them one inside the other, better be inverse functions. So in other words, okay, g of f of x, okay, when you put the exponential inside of the log, you should produce x. You can see here, I'm putting the exponential inside of the log, I produce x. And flip of it, I'm taking log base b of x, and I'm raising it. Okay, so I'm taking that log base and I'm putting it inside the exponential, and again, I produce x, which again is good because it's going to pay us to be useful, okay, later on. For example, what if I give you something like this? Okay, it says find the inverse of y equals a to the x. Okay, we're going to treat it exactly the same way as we did any other inverse that we solved, as long as it wasn't a model. What did we do first? We switched x and y. Okay, so the first thing I want to do is I want to switch it, so I'm going to say make it x equals 8 to the y. So I'm going to switch x and y, and then just like we always did, go ahead and resolve for y. The problem? I can't resolve for y because the y is in the exponent. So you got to ask yourself, well, how do I get out of the exponent? Well, change it to log form. Okay, so if I come over here and say, hey, I want the log equivalent, I'm going to do log and put an equal sign. Again, I want to fill in 3 numbers. Okay, the base is still 8, so I'm going to put log base 8. Remember, it's of the answer is equal to this. So log, or 8 raised to the what, and it looks like it was y, has to give me x. 8 to the y has to give me x. So I think the inverse function is y equals log base 8 of x. Let's try one more. What if I do y equals ln to the x minus 4? Okay, again, the first thing I'm going to do is I'm going to switch. Okay, so I got x equals ln to the y minus 4. Okay, first thing I want to do is I want to get inside the parentheses. So in other words, I want to get rid of that natural log. So it might be first useful to go ahead and change it back to what it originally was. Natural log is log base e of y minus 4. So if I look at something like that, I got to ask myself, okay, how do I get rid of log base e and get that away? I don't want to deal with it anymore. I want to get inside there. Well, in order for me to get rid of log, I can convert it back to exponential form. So do your cycle. E to the answer, or base to the answer, is equal to whatever you're taking the log of. So if I do that, I really have e to the x is equal to y minus 4. Okay, the base to the answer is equal to whatever you're taking the log of. Now, it's one more step. How to get y by itself? I'm going to add 4. I'm going to add 4. Notice it's not part of the exponent, so I simply have e to the x plus 4 is equal to y. Okay, I've solved for y. I think that is my inverse function of the original y equals natural log of x minus 4. I'm going to let you read this, so go ahead and pause the screen and take a look at it. But we'll pick this up tomorrow in class, and we'll actually explain and answer numbers 1, 2, and 3. But give it your best shot, read the right side, and try and answer 1, 2, 3 for tomorrow. We'll see you tomorrow, and have a good night.